Welcome to College Algebra. In this lecture video, we're going to talk about something called the logarithmic functions and their graphs. So what is a logarithmic function? It is actually the inverse function of an exponential function. So as you can recall, back in Chapter 3 lecture video series, we talk about inverse function. It got to be a one-to-one functions in order to have its inverse. So if we go back to 5.1 and look at graphs of these exponential functions, okay, this one that we draw, okay, so for this exponential function to have its inverse, it got to be one-to-one function. And the way to test one-to-one function is using the horizontal line test. So if the horizontal line cross over my graph only at one point, then the function is one-to-one. If it's one-to-one, then I can have its inverse function. So normally our exponential function is a to the x power, and now we will actually find its inverse, which is my f inverse of x, which become the logarithmic function. Okay, so what's a log function? It's just an inverse of exponential. So we will read our log function as logarithm with the base a of x. Okay, so if you ever wonder what a log function is, it's just an inverse of an exponential function. Alright, so on the calculator, real quick, on the calculator, the word log, L-O-G, okay, is automatically assumed as with the base 10, okay, it's assumed as a base 10. Alright, another type of logarithm is called the natural log, okay. Natural log is basically changing the base from a regular base a, from a regular base a to a base e. So if I change my base to the number e, okay, we actually get what we so-call the natural log. Okay, so what's a natural log? Natural log is a logarithm with just base e. All right, so let's look at some properties here. These properties are coming handy from time to time. Okay, so I got here parallel between regular logarithm and the natural log. Okay, log with any base of 1 is always 0. Okay, so natural log, remember now, natural log is just a log with the base e. So log with the base e of 1, or call the natural log of 1, is always equal to 0. Alright, log with any base b of itself, okay, is always equal to 1. Let's look at this one down here. Number 3, log with any base b of itself to an x power, my answer will equal to x. So what that kind of tell us is the log with the base b of itself kind of cancel each other out. So the only thing left over is just my x. Okay, so natural log with the base in the natural log of e is equal to 1. That makes sense because natural log is the word log with the base e of itself. They kind of cancel each other out. So what's the exponent here? The exponent is actually a 1 there. So if they kind of cancel each other out, the only thing left with is just a 1. Okay. So same thing here, natural log and e kind of cancel each other out. Okay, they are inverse property to each other, so they kind of cancel each other out. So the only thing I got is x. Alright. Vice versa, what happens if my base b is raised into the log with the same base of x? Again, they kind of cancel each other out. So the only thing left with is just the x. Okay, that's the basic properties. They come in handy from time to time. Now, another big thing I want to introduce, other than what I mentioned before, where the base are the same and base are equal, we set the exponent equal. This one is called the conversion between your exponential and your log equations. So if I have a log with some kind of base a of x, what I can do is set them equal to another variable. And once I've done that, to convert into exponential, all I need to do is bring my base a to the other side of the equal sign. And then I get myself x equal to my base a to the whatever y power is. Okay. So basically, every logarithm problem, we can actually look at it as an exponential equation. Alright, for example, this one is real neat. Log with the base 3 of 5th root of 9. Okay, the reason why I cannot enter this in a calculator, because every time when I press log, base is 10. This is a base 3. So what I'm going to do here is set my logarithm equal to another variable. To convert my logarithm into exponential, all I'm going to do is bring my base 3 to the other side of the equal sign and put it in the bottom as a base. So what I got myself here is a 5th root of 9 that is equal to 3 to the y power. Alright, I'm going to rewrite my 9 as 3, as using a base 3. So 5th root of 9 will be written as 3 squared. Alright, so now I'm going to write my radical as in terms of a fraction exponent. So denominator determines the roots. So that will be 3 to the 2/5 power. So once I see the base are the same and the base are equal, I can set the exponent equal to each other. So my answer, y is equal to 2/5. Okay. So once I noticed I can make the base the same. Once I see this, once I notice I can make my 9 into base 3, I'm going to try to make the base the same so I can set the exponent equal to each other. Alright, this one here on the right. I have no idea what the answer is, so what I'm going to do is set it equal to y and bring my base 18 to the other side. So that gives me 324 equal to 18 to the y power. Okay. And I wonder, can I make 324 into a base 18? I don't know 18 very well. So let's see, what's 18 squared? Ooh, 324, got lucky here. So 324 is 18 squared. So my y is equal to 2. So what that's saying is log with the base 18 of 324 is equal to 2. Okay. Kind of hard to comprehend how the answer got to do with logarithm. And the reason is logarithm, we actually don't look at logarithm as itself. We're actually thinking about logarithm as in terms of exponential. Okay, so looking from the exponential perspective kind of makes sense why the answer is the way they are. But if you just look at the answer and trying to matching up what the problem is trying to say, it gets a little bit strange. Alright, I'm going to show you another way to do the same problem. Okay, and this kind of go back to the property too. Now after knowing 324 is 18 squared, I can rewrite my left hand side here as a log with a base 18 of 324 is 18 squared. So since my logarithm with the base 18 of itself, they can kind of like cancel each other out using the inverse property. So that's why my answer would just be true. Okay, let's look at it from another perspective. Alright, log with any base of 1 If you look at the property, the answer will be 0. Okay. Alright. Now this one, I got 2 different logarithms, so I'm going to do the most inner one first. Okay. So I'm going to look at that one first. Let's see what that is, and I'm going to put it inside that parenthesis. Log with the base 16 of 4. Alright, I'm going to set my logarithm into a variable equal to a variable y, and I'm going to bring my base 16 to the other side. So I get 4 equals 16 to the y. Alright, I can make my 16 into a base 4. That becomes 4 squared. But on the outside of my 16, there's a outer exponent y. So by the power rule, this is going to be 4 to the 2y power. Okay, equal to 4 to the first. So since the base are the same and base are equal, we set the exponent equal to each other. So my y is equal to 1 over 2. Alright, that means this log with the base 16 of 4 becomes a half. Alright, and this is log with the base 2 of 4. So I can set this equal to y, bring the base over, or I can just look at this and say, well, if I will flip my base 2 back up to the other side, I can get log with the base 2 of 2 to the negative 1 power. So in a way, log with the base 2 of itself kind of cancel each other out. So my answer will just be negative 1. Okay, so the final answer for this problem will be negative 1. Alright. Let's try this again. Alright, this is log with the base 1/4. Okay, of 16. I'm going to set it equal to y. I have no idea what the answer may look like. Alright, I'm going to bring my base to the other side. So I get 16 equal to 1/4 to the y power. I'm going to put a parenthesis on my 1/4. Okay. So I see that 16, I see that 4. Can't help it, trying to make the base the same. I know 16 can be 4 squared, but the base 4 is on the numerator. So that means this 4 in the denominator can be flipped back to the top. That becomes 4 to the negative 1 power. But since I have an outer exponent y on the outside, I can then this will become 4 to the negative 1y power. So that means once I set my exponent equal to each other, my y will equal to negative 2. Okay. Alright. Now when I see this particular problem, I know from the inverse property, natural log and e will cancel out. So I'm going to rewrite my middle into a fraction exponent. So that means I should have natural log, okay, with the base e of denominator determines the root. So that will be 5 over 8 power. Okay, so natural log and e kind of cancel each other out because natural log is log with the base e of itself. So they kind of cancel each other out. My answer would just simply be 5 over 8. Okay, so we can do all these problems without using a calculator. Okay, because calculator doesn't really come in play that much right now. Okay, it's because I can actually manipulate these. I can actually convert most of these into exponential equations, or I can try to make the base the same and where the base will cancel each other out using the inverse property. Now this group of problem is a little bit different. Okay, all right, this is log with the base 10 of 2078 equal to 5x. So technically what I can do is put this in the calculator, give me some sort of numerical value, then I will divide both sides by 5. So I'm going to do it that way, but I'm just don't write it out that way because I know log of this number is real nasty. So I'm just going to go ahead and divide both sides by 5. And what I will key in the calculator will be the log of 2078 divided by 5. Alright. Just be careful how we enter this in the calculator, because every time I press the word log, it gave me a parenthesis. So this whole numerator is actually treated as one term. So my 2078 got to be in the parentheses, so don't forget to close it. So the calculator will figure out the logarithm first, then we'll divide it by 5. Okay, we'll write it as 2 decimal place. That'll be 0.66. I don't think these can be converted to a fraction. Nope. Alright, take a look at this one. Now for this particular problem, I am going to use conversion between log into exponential to help me. And this is one of the techniques we can use to solve logarithm equation. Because there's no way I can make the 5 like a base 2 down here. So think where things can cancel. So I'm going to bring my base 2 to the other side, and I'm going to look at this from exponential perspective. So this is going to be 5x equal to 2 to the 4 power. So what I'm looking at right now is actually a linear equation. So to get x by itself, I just divide both sides by 5. So that will be 2 to the 4th divided by 5. So that would just be 16 over 5, or you can say 3.2. Okay, that's how it is. Looking at it from the exponential perspective. Okay. Alright, this one is interesting because this is a log with a base 10 of e to the x power. So this is not a natural log. This is just a regular log with a base 10. So again, I'm going to convert this into exponential equation and go from there. Move my base to the other side of the equal sign. So I can have e to the x equal to 10 to the 19.1 power. Alright, now how do I bring this x down? Okay, because this variable x is on the exponent. So here is where these properties come in place. Alright, I know natural log and e can cancel each other out. So if I will take a natural log on both sides, okay, natural log and e will cancel out, leaving with the x. But if I take a natural log on the left, I got to take a natural log on the right side as well. So natural log and e cancels out, so that leaves me with just x equals natural log of 10 to the 19.1 power. Okay, let's see what that would be. So when I press natural log, it gave me a parenthesis. So remember now, natural log just a log with a base e. Alright, in the inside, 10 raising to the 19.1 power. Alright, 2 decimal place, that would be 43.98. Alright, so our techniques are convert them into exponential and solve it from that perspective, or I can take I can convert log into an exponential And if I have e, I can take a natural log on both sides. Okay, that can actually isolate my variable for me, because e and natural log always cancels out. Alright, so this one right here, again, everything is two terms. So far, everything we've done in this video is two terms, so it's not bad. It makes it a lot easier. So I have no idea what this is, so I'm gonna just, using the techniques that we already learned, bring my base to the other side. I'm going to look at this from exponential perspective. So once I bring my base 9 to the other side, what that leave me with is this: my 2x minus 1 is equal to 9, my base 9 to the second power. So now this equation becomes linear equation. So this is going to be 2x equal to 9 squared is 81. 81 plus 1 is 82. So my answer, 41. Okay, that's all it is. Go through some of these. Same thing here. It's probably very interesting. This is a natural log. So I'm gonna write this down. You don't have to copy this for me. Okay. So this is natural log, is log with a base e, right, of 7x plus 8 equal to 3. So what I can do is bring my base e to the other side, and that will convert into an exponential. So that will leave me with 7x plus 8 equal to e to the third power. Okay. So that being said, okay, another way to do this is basically opposite direction of this previous one. So since this whole left side is only one term, to get rid of the natural log, what I can do is take an e on both sides. Okay, remember now, e is a base, so if I'm taking the e, that means I'm bumping everything to the exponent, because I know e and natural log will cancel out. So that just leave me with 7x plus 8 that was on the exponent equal to e to the third power. Remember now, e is a base that will bump up my 3 that was there to the exponent. Alright, so I'm going to move my positive 8 over. That gives me e to the third power minus 8. I'm not going to key this in the calculator yet. I'm going to do it all at one time. To get x by itself, divide both sides by 7. So that's e to the third minus 8 divided by 7. So I want my calculator to figure out the top before you get divided by the bottom. So I'm going to purposely open a parenthesis for my two term on top. Second, e to the x. Okay. Put a 3 in there. Close parenthesis, so that's my e to the third minus 8. Close it. For my numerator, then divided by 7. 1.73. 2 decimal places. Okay. I know this answer cannot be converted back into a fraction, because when I have an e right here, e is an irrational number. So any operation after that will probably be irrational. Alright, let's try a couple more. Alright, this whole left side is one term. So when I see natural log and e side by side, that automatically cancels out. Now, I'm not taking a natural log on both sides myself. This natural log is already there, so they can just cancel out. My answer, x equals 15.2. Okay, this is different than earlier when I take a natural log on both sides. Okay, this natural log already there. Alright, this is an interesting little problem. This problem can be done a lot quicker. It depends on which technique you want to use. I can bring my base 2 over to have 2 to the 5th power on the right side. But when I see this 16 and notice my log is using a base 2, I cannot help myself but to rewrite my 16 using a base 2. Okay, the 16 can be written as a base 2 to the 4th power. 2 times 2 is 4. 4 times 2 is 8. 8 times another 2 will be 16. But remember now, on the outside of 16 there was a 6x power. So by the product rule, we can multiply the exponent and say this is 2 to the 24x power equal to 5. So my log with the base 2 of itself kind of cancel each other out. Okay. If it does not cancel each other out, bring the base 2 over here will make the base the same, so the exponent will still equal to each other. So either technique will work. My answer, 5 over 24. This one is pretty easy because inside the parenthesis here just an x. So all I'm going to do is bring my base over using the convert them into exponential. That will put me at 32 raised into the 2/5 power. Be very surprised what this answer is, because 5th power means 5th root, and 32 is actually 2 to the 5th power. Okay, 32 is 2 to the 5th power. So the 5th power and 5th root will cancel out. That's why the answer is the way it is. 32 raised into the parenthesis 2 over 5. My answer, 4. Okay. Right, 32, 2 to the 5th power. 2 over 5 power on the exponent means 5th root. Okay. Square means that my whole thing can be what? Squared. That's why 2 squared will be 4. Alright, this is a very interesting little problem here. There are a couple ways to go about doing this. Okay. I think the quickest way is by saying make 64 into a base 4. Without complicate too much, it's going to be log base 2 of x equal to 4 to the 3rd power. 4 to the 3rd is 64. So now I can set the exponent equal to each other. So that gives me log of the base 2 of x equal to 3. And once I bring my base to the other side, that will leave me with 2 to the 3rd, which is 8. Okay, that's one way to do it. Another way to do this is actually trying to make this base 4 into a base 2. Because if this becomes base 2, that becomes 2 squared, right? 2 squared is 4. So since outside of my base 4 has a exponent, which is log with a base 2 of x, okay, then I can use the power rule, say this is 2 to the 2 log with a base 2 of x. So what's going to happen is the log with the base 2 and my base 2 down here will cancel out. Okay. So technically that will actually leave me with 2x. Okay, but not really. Can't really do that because not thinking about it, I don't think it's as legit as I want them to be. Right now my mind is want to see something that may not be there. Alright, let's check it out. See if it still come up to be the same. Alright, make 64 into a base 2. Think about this. 2 to the 5th power is 32 times another 2, that becomes what? 64. Okay, so this is 2 to the 6th power. So this is 2 to the 6th power. So right now I really can't do too much. Well, yes I could. Divide both sides by 2. 2 to the 6th power is 64. Divide both sides by 2. My answer is actually 32, which is not right. Okay, the answer is 8. Okay, so this way is not really legit. I think what goes wrong here is actually right here. When I cancel them out and say what's left over is 2x, I don't think it's 2x. I think it's x squared. Which y is x squared? Tell you in the next lecture video. So I'm gonna write it this way. I'm gonna write x squared. It's actually x squared. So this is 64, right? Take a square root on both sides. My answer will be 8. Right. Oh, that reminds me of something. Because normally when we take a square root on both sides, my answer is positive negative 8. Why don't I pick negative? Because if I do a logarithm, don't matter what the base is, of a negative number, it's actually not a real answer. Okay, it's actually undefined. Okay, cannot take a log of a negative number. Alright, what about the property here? See, none of the property also including 0. So if I take a log of any base of 0, it will actually not define this way. Okay, cannot take a log of a negative number. Gotta be positive. Alright. But I will show y'all why this become x squared here, okay? In the next video. Alright. Now, so far everything, works out on this page. I either convert my logarithm into a exponential and solve it from there, or I can somehow make the base that are the same, log with the base 2 of 2 here, so that they're saying they cancel each other out. Okay, I can take a natural log on both sides, take an e on both sides. There are just different techniques to go about doing these problems. Okay, so these little techniques, I run through are your approach, but in a different section I will actually write down all these different approach. So there's one more type of problem we have not run into, which is problem look like this. Which is actually a problem that where you cannot make the base the same. For example, picking on this particular one. Where's my 1/4 power earlier? Sorry, we'll scroll through this. See this right here? Okay. This particular example, where it's eventually the 16 worked out for me because I can make my 16 to a base 4, where the base can become the same, where I can set the exponent equal to each other. But what happens if this is not a 16? What happens if it is a number that I cannot make the base the same? Then another technique is called a change logarithm basis. Okay, but in this objective I'm going to use it for graphing. If I ask you to graph log with the base 5, there's no way you can key that in, because every time we press log, the base is 10, but this is a base 5. So what we're going to do is changing our bases. So a log with the base b of m, where m got to be positive, b and a are your bases. Then we can convert them into log with the base a of m over log with the base a of b. So b is going to be whatever that base is. M is whatever I'm of. But what's base a? Base a can actually be 10 or base e. If I use a base e where the a is at, that gives me a natural log. So this is where it's crazy. Okay, remember now, one of them is going to use base 10, one is going to use base e. Alright, so if I will match up this formula with this part right here, b gotta be my base 5, m gotta be my x plus 1. This minus 1 just shift my graph downward one place. So if I will change the base, that will be log with the base a of m. A can be base 10 of m, which is x plus 1, over log with the base a. A can be base 10 or base e. I'm going to use base 10 for right now. Of b. B we say is 5. Okay, so I'm changing base 5 to a base 10 on my graph. Now, if I were change base a to an e, that becomes natural log. So that'll be natural log of m over natural log of my b, which is 5. And this is crazy. Watch this. Alright, my numerator. By the way, this whole top is actually one term. So when I press log, it's automatically one term. Of x plus 1, close parenthesis for my x plus 1, divided by log of base 5. Log of 5, close parenthesis. y2, I'm going to type in natural log. Okay, using a base e. X plus 1, close parenthesis for the x plus 1, divided by natural log of 5. Standard window. Take a look. Oh, sorry, forgot the minus 1. I'm sorry. Supposed to minus 1, 2. So let's go back out. Ooh, if I have a minus 1 there, that will actually, that means I gotta insert a parenthesis at the very beginning for my first term. After tapping my 5, I'm gonna insert another one. I gotta close one, then minus 1. Sorry about that. Getting too excited. Okay, minus 1. Alright, so let's shift down 1. I enter 2 different lines, 2 different equations. And that's it. One graph. Okay, I'm going to make my window a little smaller. My y value, I'm going to go from -5 to 5. Make the picture pop a little bit. There you go. That's it. I type in 2 different equations. It's only one line. So that tells you that the 2 are exactly the same. That's very, very strange. One is using base 10. One is using base e. But it gives me the same thing. Okay. So that's the reason why I say we can use base. For my base a here, I can use 10 or e, because it gives me exactly the same graph. Alright. So let's try this one, okay? This one doesn't have that minus 1. Doesn't have any vertical shift here. So, if I'm matching my formula, this x minus 1 got to be m, b got to be 1/3. So changing the base formula, that will be log of m. So my base is 10 now. Alright, over log with the base 10 of my b, which is 1/3. So I can do it using log or natural log. So I'm going to type in natural log. So natural log of x minus 4 divided by natural log of 1/3. So I can, I'm keying natural log. Maybe you can key in log and look at our graphs. It will be exactly the same thing. Okay, let's go in this direction. Okay, let's go in this direction. Alright. By the way, I do want to just kind of graph part of this to demonstrate. Okay, to demonstrate. what I illustrated at the very beginning. What is a log function? A log function is nothing but an inverse. Okay, it's nothing but an inverse of an exponential. So if I would just simply graph, I'm just using the top right here. Okay, if I just type in log of x minus 4, here is what my exponential function looks like. Excuse me, that my log function looks like. Okay, these are the graph of the log function. Alright, so it's a one-to-one function, so that means I have its inverse. So rather than find the formula for the inverse of this, okay, well I can, because this is a base 10. So if I want to find its inverse, I'm gonna purposely write 10 right here. Alright, set it equal to y, move the base over, so I get x minus 4 equal to 10 to the y power. Okay. Alright. Interchange between the x and y variable. So that will be y minus 4 equal to 10 to the x. Solving for y, that will be 10x minus 4, excuse me, 10x plus 4. Alright, so this will be my inverse of that. So if I just say 10 raised into the x power plus 4, okay, it'll be right there. Let me go back to my regular window. Remember, when I interchange between the x and y variable, I'm also interchange between the x and y coordinates. Let's come smaller. Whoa. Okay. Negative 5, 4. Now if I got negative 5, 4 for one, I should have 4 negative 5 for another one. Oh, it doesn't exist. Maybe I did it wrong here. Anyway, what I really want to show you, maybe the way I found the equation is incorrect. What I really want to show you is the way to draw its inverse, okay, but without finding the equation. So once you grab this graph, we can actually go to the word draw, second draw, okay, and go down here, find the word say draw inverse, right there. Alright, draw inverse of my y1, okay, because I put my log function under y1. So we can say vars, go to y-vars, number 1 function, and then extract my word y1 and press enter. That'll be right there. So I did find my equation in the wrong way. Alright, so now when I look at my coordinates, 5, 0, okay. Well, I'm not gonna have 2 of them. Sorry, because I draw the other one. I don't have another y because I didn't put it in the y equal. But these 2 are inverse to each other. Okay. Alright, I just want to show you the graph of logarithm and its inverse without finding the equation. Alright. So y equal, I thought I could do it, you know. Y equal interchange between the x and y. Yeah, maybe I should have interchanged the x and y ahead of time before I move my 10 over. Alright, but that's not the point. This is something extra I want to show y'all. Alright, in the next lecture video, we will talk a little bit about, okay, problems where I cannot make the base the same, where we got to come back and use the change of base formula. Alright.